Well, this doesn't make sense for a chart because I don't have 8.001 is not one of the numbers on my chart. The only numbers I can plug into f are these 6 numbers they gave us. So, like, I can't compute the derivative. The idea we need to focus on is the reason we picked 8.001 is it's very close to 8. We're sort of thinking, can we get as close as possible? When we did it for, when we have a formula, there is no as close as possible. I can stick more and more zeros in here, and they will all get closer and closer. There is a point where my calculator stops making sense of it. If I plug in 8 with 30 zeros and a 1, my calculator is not going to give me any meaningful information. So there is kind of a limit that's hard to trace, which is a technological limit, not a mathematical limit. For the chart, though, this as close as possible comes to have a very specific meaning. What is the closest number to 8 that I'm able to plug in? Well, the numbers I can plug in are 0, 2, 4, 6, and 10. The ones that are close to 8 are the 6 and the 10. Which one's closest? Oh, they are tied for closest. What do I do when it's tied for closest? Well, if there's no other reason to pick one over the other, like maybe if I was using this because I wanted to know what's happening a little bit bigger than 8, so the 10 is more important or something. If it's not the case, if it's a tie, do both of them and split the difference. A lot of the times in the homework they'll tell you use the right hand number, so if it tells you, then do that. If it doesn't tell you, do it both ways and average those two answers, and that's your best estimate. So I want to take f of 10 minus f of 8 divided by 10 minus 8. I want to take f of 6 minus f of 8 divided by 6 minus 8. This gives me 19.2 minus 18.1 divided by 2. I subtract that, that's 1.1 over 2, that's 0.55. So I've got that f prime of 8 is about 0.55. F of 6 minus f of 8 is 17.3 minus 18.1 divided by negative 2. What is that? This is negative 0.8 divided by negative 2. The negatives cancel and I get positive 0.4. So this computation says f prime of 8 is about 0.4. Which one do I trust more? I have no reason to trust either one more, so I average those two numbers. That's 0.95 over 2, that's 0.475. That's our best estimate, is that f prime of 8 is about 0.475. It's about 0.475. Boom. Cool. The key thing to keep in mind is the reason we plug in these 0.001s is we want to get as close as possible. When you can't get as close as possible, well, that just changes what as possible means. There's a real sense that this is much less of a real derivative than the other one is, which is fine, and it sort of makes sense to think of this chart as less of a function than something where all the numbers are defined. But when someone talks about the derivative of a chart, this is probably what they're talking about. Let's talk about this in terms of a graph. The graph one is extra weird because in the graph context, we kind of find out that our idea of a derivative does something different than the reason we wanted it. We wanted to ask how fast was something going. I mentioned at the time that the rate of change gives you the slope. So what we're basically asking is, what is the slope of the graph at this point? And just like with that rate of change, you can't figure out a slope from one point. The way you compute a slope is you subtract the y's and subtract the x's. If I only have one point, I only have one x and one y. If I subtract those y's, I'll get 0 on top, 0 on bottom. I'm in the exact same situation I was in. The thing we want to do is, instead of finding the slope at this point, we pick a nearby point. and say, that's pretty close to the graph. If I drew this line, this is called a secant line, is a line that hits a graph at two specified points. That's pretty close to the slope of the thing at the point, and if that t moved closer to the point that we care about, I can imagine this line, like if I drag this point even closer and closer to there, then that blue line will tilt down, down, down until it turns into the purple line. And that's the idea going on. The way we would approximate the slope of the graph at a point is the exact same way with the exact same definition. And the thing we're getting to is this purple line is called the tangent line. The tangent line is a tricky thing to define, and I'm bad at it. Or, mathematicians are bad at it. What's the tangent line to a graph at a point? The idea of the tangent line stylus problems. So the tangent line is a tricky mathematical concept. It's hard to come up with a correct definition to it. The idea that you want to say that it's the line with the same slope. This sort of passes the buck along of what does the slope of the graph at the point mean. Well, what it means is what's the slope of the tangent line. That's not a good definition. Sometimes people will say that it is the line that only hits the curve once. This is a good definition for a circle. If I take a circle, and I could do a better circle than that. If I draw a circle and I think about all the different lines that go through that circle, they will basically always hit the circle one more time. There's only one way to draw a line that only hits the circle exactly once, and that's called the tangent line. If you're a little bit off, then you're going to intersect the circle someplace else. Well, that definition works for a circle, but for other curves, hey, this only hits it the once, but it's going to hit it again somewhere else. It's still the tangent line. This thing about only hitting it once only really works for circles. You can get even better by saying, the important thing about the tangent line is that it touches the point without going through the curve. Maybe this will be the definition. Any other line crosses the curve at that point, but the tangent line is the only curve that glances off of the curve without passing through it. And that gets at the important thing most of the time, but it's not good as a definition because I can draw a curve. Let's see. Let's draw the tangent line first. I can draw a curve that is going the exact same direction of the line, curving this way on one side, but curving the other way on the other side. And now this thing is the tangent line, but it does cross through the curve. It was above the curve, and now it is below the curve. It did pass through. This is a rare situation. Most curves this doesn't happen. This is going to be called a point of inflection when we start talking about points of inflection. So that's also a bad definition of the tangent line. How do we get a good definition? Well, we cheat. The tangent line to a graph at a point, a graph of a function, let's call it f of x, at a point, let's call it x naught, is the line that hits the point